So, Chemistry 3053, let's continue with our chapter on radicals and their reactions. So, here we are, sections 10.7, 8, and 9, allylic bromination, atmospheric chemistry and the ozone layer, auto-oxidation, and antioxidants. So, let's first look at the allylic bromination. Remember, bromination is a reaction that is very regiospecific. And so, here, let's look. The alkenes selectively undergo hydrogen abstraction at the allylic carbon. Here it is. And look at the bond association energies of each of these hydrogens. This is vanillic hydrogen, allylic hydrogen, and just a typical alkane hydrogen. So you can see, compared to the bond association energy of the typical alkane hydrogen, the typical CH bond, the allylic position hydrogen has a much weaker bond. It has a lower bond association energy because it gives rise to the allylic radical, which is much more stable. And in the reverse, the vinyllic CH bond, when cleaved, has a bond association of 444 kilojoules per mole. And so that is higher, much higher than the other two, and that's because this would create a vinyllic radical where the unpaired electron is in the sp2 hybridized orbital and much higher in energy. So this gives the most stable radical, which is the allyl radical. And so that's what we're going to look at now. Will be reactions that go through that allylic radical. And so, here, let's look at this. So, hydrogen abstraction, by some, radical generator. So, here you're going to have the abstraction of H dot to leave the unpaired electron at the allylic position. You can see that it's stabilized. Here, there's a resonance stabilization. And remember, bromination is much more selective than chlorinations, which we just saw in the last video. And so looking at bromination, you will get exclusively bromination at the allylic position. And so here, now this is allylic halogenation with N-bromosuccinimide. Now let's go back and look at this. Look, here, this is with Br2, with just molecular bromine. And so you could envision in this, you could also have addition of bromine across that carbon-carbon double bond as a competing reaction. And so a way to reduce that, so here we use N-bromosuccinimide, and the N-bromosuccinimide, this is a heteroatom bond. Remember what I said earlier about heteroatom bonds are particularly weak, and so they often can be cleaved to be used in a radical generating reaction. So this is your initiation step here. Light cleaves that bond, and you have radical on nitrogen and on bromine. And so you can use this, and so you'll see in the next few steps we're going to generate HBr and Br2, because when the bromine Br dot comes in to let's see if it's, yeah, when Br dot comes in to pluck off a proton, HBr is going to be generated. So you want to keep the HBr and the bromine concentration low in order to minimize addition across the carbon-carbon double bond. We want to maximize formation of the reaction at the allylic position. And so using this will accomplish that. So this is very good use of the N-bromo-6-enamide, often abbreviated as NBS, is used a lot for allylic bromination reactions in synthesis. And so here it is. You will have Br dot from the initiation of the reaction using NBS, and it will abstract H dot, leaving the allylic radical, and here you have some HBr generated. And so this reacts with another molecule of N-bromo-6-enamide. Here we are. It reacts with another molecule of N-bromo-6-enamide to give you just 6-enamide, where this is an NH bond, and Br2. So so when that happens, you have Br2 reacting with your allylic radical, and that gives you bromination at the allylic position. So here also you can see this is going to be a stable radical generated, and so it will be, you will abstract proton here, and then you'll have the allylic radical, and then you can have the second step occurring either here or at the other end of the alkyl chain. So you can have bromination occur here or there. And that's using the N-bromo-6-enamide. Now, atmospheric chemistry and ozone. Ozone is created and destroyed in the upper atmosphere. No net reaction occurs overall, but the UV radiation from the sun is converted to heat. So, global warming. And so here you have ozone converted to molecular oxygen and just atomic oxygen. So note, you have atomic oxygen that are interconverting here. And so pay attention to O3 and atomic oxygen. Keep that in mind in the next couple of slides. Heat is a more disordered form of energy compared to light, so the process is spontaneous because entropy is increased. And the ozone is depleted. It is a serious health and environmental problem, as you already know. Without it, the harmful UV radiation penetrates the atmosphere directly to the Earth. So chlorofluorocarbons are believed to be the culprit. You're going to see that in the next couple of slides. We'll look at the mechanisms. Here they are. This is different kinds of freon. They reach the upper atmosphere and react with UV light to form chlorine radicals. Notice each one of these has chlorine atoms in them. And it's the chlorine atoms that are the problem. The chlorine radicals that are formed from the light, you can see the bond breaking. This is the initiation, and you get Cl dot out of that. And here is the mechanism by which they destroy ozone. Remember I said to pay attention to the O3. Okay, so now we have Cl dot reacting with O3 to give you ClO plus O2. And then the ClO reacts with the atomic oxygen that I told you to pay attention to a couple of slides back. So we have both O3 and the atomic oxygen being reacted here. They're being consumed. And so that's the depletion of the ozone. So this gives rise to oxygen and Cl dot, which you're regenerating them there. And so this is the propagation step. So ozone is being depleted and Cl dot is being regenerated. And so that's the way you have the destruction of ozone. And so there are some attempts to replace the chlorofluorocarbons with just hydrofluorocarbons. And here's a couple. These are more expensive. They're not as harmful because they don't produce chlorine radicals, but they're still greenhouse gases. And they're also not as effective. And they are more detrimental to some people who need, and more expensive for some people who need the drugs that were used or were based on the chlorofluorocarbons. Now, autooxidation is the process by which organic compounds react with atmospheric oxygen to form a hydroperoxide. So, for example, cumene can react with O2. Right here, you're going to have a very stable radical center formed, possibly, because this is not only a tertiary carbon, but it's also stabilized by resonance. And so this is a cumene hydroperoxide. Now, this is very slow, but nevertheless, this is the type of reaction that you have that is autooxidation, and it can take place in things like your cereals, your peanut butter, and other compounds, and it can be responsible for giving an off flavor, a bad flavor to your foods. And so, for example, in the case of peanut butter, you can simply avoid this. Keep your peanut butter in the refrigerator. It will really slow down this reaction. And so here's the autooxidation mechanism. The initiation step is actually one of the 6 types of propagation steps covered earlier, but remember what I said is that those are just the most common steps. They are not exclusively the only steps. You have to be flexible and remember that as these things are being presented to you, just the most common steps or the most common situations or the most common uses are being given to you because that's what you're going to see most likely if it's the most common one. So here we have an initiator. It could be oxygen from the atmosphere, plucking off H dot and leaving the carbon radical. Then the carbon radical reacts with oxygen to give you this peroxy radical. Then you have the hydrogen abstraction by the peroxy radical to give you R dot. And so here is your propagation. Okay? And the termination is just the coupling of 2 R dots. It destroys the 2 carbon radicals. And so this mechanism, although it does have a different initiator than what you saw earlier, what you saw earlier was just a simple homolytic bond cleavage. That's obviously not the only type of initiation that exists. Here is one example of a different type of initiation step. The homolytic bond cleavage is the most common one, and so that's what you've seen mostly. But so that's a little bit different. It doesn't exactly fit your 6, what you saw back when we were covering the 6 different types of mechanistic steps. But this chain reaction mechanism does have the initiation, propagation, termination, and indeed the propagation consumes the reactants and produces the products, and it also regenerates the intermediate that has to be used in the next step here and here. So it does fit the definition of a radical chain reaction in that way. And here you see what I just said with it drawn out as two different steps here drawn out in this way, and you can see that the steps that are where you're regenerating the reactant to be used in the next step are excluded, and you simply add up the reactants and the product, and you can see the reactants are being converted to products, and so that fits the definition of a radical chain reaction. Notice that initiation and termination steps are not part of the net chemical equation of a radical chain reaction, as shown here and before. Autooxidation. Ethers are particularly susceptible. This is diethyl ether, which is a solvent commonly used in lab, and if it sits around in a lab for too long, this happens, and those are explosive. The hydroperoxides are explosive, and so you don't ever want to go down and buy a huge amount of ether just to put it up on the shelf and expect it to sit there for a few years. So usually small amounts of ether are purchased and consumed, therefore, fairly rapidly. Sensitive compounds can also be stored in dark containers, and it prevents the light from accelerating this process. You can use dark colored glass, you can wrap it in aluminum foil, whatever. Triglycerides are important to a healthy diet, but also susceptible to autooxidation. And that's because they have these allylic carbons where you can get the peroxy groups formed, and these are not good for you to ingest. And this is what happens in some of your foods. If there's not a preservative, or even if there is a preservative, it can still happen after a long time. So you don't want to buy huge amounts of foods that will have this happening, and then you eat them. The other alternative is to store your food where there's a high likelihood of that happening. Store it in the refrigerator or in the freezer, and it will cut down on this process. Foods with unsaturated fatty acids have a short shelf life unless some preservatives are used, and these are typical of the preservatives: butylated hydroxytoluene, butylated hydroxyanisole, and these prevent the radicals from being formed. Notice that what they have is they have an H dot that can be abstracted here. H dot can be abstracted, and when that happens, the oxygen radical is very highly stabilized by resonance. Okay. And I might just point out, do you see these large T-butyl groups on both sides, or on one side, or on the molecule itself? Well, those are there to keep these things from simply dimerizing, reacting with each other, and consuming each other. So these are, the steric hindrance here will prevent these things from reacting with each other. So this one molecule of this, when it reacts with R dot, can stop that chain reaction. It can block this alkyl radical from taking place from participating in a radical chain reaction, where it might, a radical chain reaction, if it could have 10,000 or 100,000 turnovers and produce, 100,000 radicals, or peroxy substituted double bonds at the alpha position. And so, these things are very important in reacting, consuming these radicals, converting R dot to RH. And so this is a very stable due to the resonance effects and also due to the T-butyl groups. So it's sterically and electronically both very stable. Okay, so in the next and final part, we will look some more at some rather specialized topics of radicals.